Yes, hello everyone. You're welcome to another video session of Python for All. In this video, we will continue from where we stopped in our previous video, and here we'll look at array operations. To start with, first we need to import the NumPy library. So we import NumPy as MP. We create an array of X and Y, which is a 2 by 2 array, and of float type 32 bits. So now first we carry out, I can add the two arrays by using the simple addition operator. So I will say print x plus y. Or alternatively, you can use mp.add x and y. So first I run this cell, I have it in my namespace, then run this. The output gives us same results. In the same vein, we can perform a subtraction operation by using print x minus y or np.subtract x comma y. Run this cell likewise, we get same result, same answer. We can also multiply the two arrays using the asterisk operator, which is a multiplication operator, or np.multiply x comma y. Run this likewise. What do we have? We have same result as output. Then here is a division operation. Here you have x divided by y, or you can use np.divide x comma y. It gives us same result as well. Next, we'll talk about scalar multiplication or the dot multiplication. Here you have three alternatives. First, you can use the at symbol, x at y, or x dot y, or np dot xy. All of these will give us the same results. So there are other operations you can carry out in NumPy, for example, np.sqrt. In other words, looking for the square root of the array. We can do that. It gives us this result. Now I want to print the shape of x, print x and the shape of x. So x is a 2 by 2, and then this is the value of the x array. What we want to talk about next is the reason why I printed this array. I want to look at the sum of the array. When we do np.sum of x, it sums all the values and returns a single value. Or we can sum along the axis 0, which is column wise, or along the axis 1, which is row wise. So if we sum it this way and axis 0 and 1, we will see the result we have when looking at the value of x. Running this cell gives me the first one is 10. The next one is 4, 6, which we see is summed column wise 3 plus 1, 2 plus 4. And when axis is 1, it is summed row wise 1 plus 2, 3 plus 4. This is applicable to NumPy arrays. So axis 0 is summed column wise, axis 1 is summed row wise. The next which you want to look at is broadcasting. What is broadcasting? Broadcasting simply put is one of the operations that is carried out on NumPy arrays, such that if you have two arrays of unequal dimension and then you want to operate on them either using the addition, subtraction, or division operator, what happens is that NumPy simply makes those two arrays to be of the same dimension by simply repeating either the rows or the columns of the other array, which will make it same dimension as the first array. So this is an example. Here I have x, which is a 4 by 3 array, and then I have v, which is a 1 by 3 array. Okay, and then here I'm calling y, which is np.zeros like x. In other words, I want to fill y with zeros of x. There are two ways of doing it. Either you call zeros like and you pass in the array directly, of by which the numpy zeros like function will extract the dimension of x, or you simply pass in the dimension directly, which is 4, comma 3. These two way. So let's see the first way. Zeros like x, we run it and then we print y. What we have, you see, y is the zeros of 4 by 3. Let's see the second way. Here we pass in 4 by 3, an array of 4 comma 3, right? Run this cell, what do we have? And print y. It gives us 2 comma 0. 1 second. Oh, sorry. When I want to use that, you should use zeros, not zeros like. So we pass in zeros. See, it gives us same 4 by 3. So it's either you use np.zeros and you pass in the array, or you use zeros like and then you pass in the array directly. Zeros passing the dimension, zeros like passing the array. So I'll go back to this, run this again, print, we still have same 4 by 3. Now what we want to do is that we want to loop in the range of the first dimension, which is the rows. Okay, and it is 4. So that's why I choose, instead of hard coding, I just chose for I in range y dot shape 0. So y dot shape 0 takes the first item, which is 4 of from the tuple 4 comma 3. So what I'll do is that for every of those rows, I want to fill them up by looking at the rows in X and adding them directly to V. So if you run this, what do we have? We can print X, we see the value of X, and then we can see the value of Y, and then V the shape is 3, 3, 3, 1, 2, 3. That's 3 columns. Okay, the role is what? 1, which is 0 in Python. That's why it is omitted here. Now, instead of doing this, is the using an explicit for loop to do this. In the same manner, we can repeat this same and do it this way. By first of all, this is the X array. We have the V, and then we call W. You know, previously we used Y, so but now we're using W. Now let's use Y here so that we have a uniform variable. So here we're saying Y is np.tile. Tile is a function in NumPy. What it does is that if we pass in the array, we want to take the array V and replicate it 4 times. Okay, replicate it 4 times. In other words, we replicate it, we'll have a single row of it. Sorry, we have 4 rows of it and a single column. So we have just 4 rows and single column and repeat it 4 times. So we stack 4 copies of V on top of each other. First one, second, third, 4 to make up the shape 4 by 3. Since this is what is a 1 by 3 array. So let's print y and let's see the shape of y. If we run this cell, what do we have? You can see it. Y is now a stack of V, stacked vertically on each other to give us 4 by 3. So this is exactly what NumPy does with broadcasting. In other words, if we call it directly, NumPy will simply broadcast the values of V to make up to the same dimension with X, and then we can now add, say call a new variable Z and say it is X plus Y, X plus V rather, X plus V, and then print Z. What do we have? If we print same result as we have done earlier, 222, 555, 888, and 1111, 222, 555, 888, 1111. Okay, what's the catch here? The catch here is that instead of using the explicit for loop, simply what now use the vectorized form, which is the NumPy broadcasting, which is done under the hook for you. You don't have to code it. Just add X to Y, and NumPy takes care of the rest by broadcasting the values either in rows or in columns. Now, another operation I want to share here or show is the reshape. We can change the dimension of any array. So now we can reshape Z and assign it to D. And then we, instead of having it as 4 by 3, we'll reshape it to 3 by 4. Mind you, the product of those two shapes gives you 12, which means that you have 12 elements there. So when you want to reshape, you can only reshape to the dimension that would, when multiplied, will give you 12. Just like here, we can reshape into 3 by 4. If I run it, what do I have? I have this. We can reshape likewise into 2 by 6. You'll see it, what will I have? It gives me this. Another way of reshaping here is that I can reshape into a 2. And if I don't know the next dimension, I can just use -1. Okay, I can call -1. So what that does is that NumPy will determine that dimension for you. If you run it, what does it give you? And when you call define the shape and say d.shape, it gives you run again, it gives you same 2 by 6. Okay, so that's one way of doing it. I've shown that here. You can flatten that array to 1D by simply reshaping into one. You want it to be a single row, and then you can determine its number of columns. If we run that, what we have the array flattened out. Okay, you can likewise do this again using what now? The Ravel function, d.ravel. If you run it again, it gives you the same answer. The question is, what is the difference between these two? The Ravel function is memory efficient in the sense that it does not make a copy of the original array. Unlike Reshape that makes a contiguous copy of the original array. So you can weigh out which one you want to use when you are writing your code. Is that the Reshape or the Ravel? The Ravel takes no input. It is flattened. It flattens into a 1D array. So next we'll talk about scalar code. And here I will illustrate with an example. First, we import NumPy as NP and we import maths. Then here I define my the number of elements I want is 101. And I'll create zeros of n and also create the array y, which is zeros of n. And then I determine the spacing of the coordinate, which is 2, divided by 100, that's 0.02. So I want x to be spaced, each values to be spaced, with 0.02 interval. So here I do a for loop of I in range n. What is xi? -1 plus delta x plus 1. Now, when I is 0, when you are looping, what do we have? We have it as -1. So we are moving x from -1 and until the last value. What's the last value? When I is 101. Okay, 101. 101 times delta x, okay, plus 1. In other words, what's delta x? 0.02 times 101. That'll give us what? That'll give us a value, right? 101 times 0.02. So that's like 1.01 times 2. That'll give us 2.02. 2.02 minus 1 will give us 1.02. So in other words, mind you, I here, the range here will stop at what? 100. So the I will be the last value will be the 100 value, which is 100 times 0.02, and that's 2 minus 1, 1. So we are looping x between -1 to 1. So there we can now call yi equals math.exponential minus xi times xi. We are doing x exponential minus x. So if we run this code and print the value of x and y, we can see what we have. We have it from -1 until 1 within a space interval of 0.02. And then we have the corresponding x value. Mind you, x times e to minus x is this value and then until 1. But what is the vectorized code of what we have just done here? It's simply using the NumPy function np.linspace -1 to 1. And how many linearly spaced vector do you want? 101 total, but it's 100 linearly spaced between -1 and 1. And then how do you perform the operation here? You don't use the math library again. We use what? NP, the NumPy library, because we are dealing with array and vectorized operation here. So we have np dot exponential of minus x times x, or you can write it as x multiplied by np dot n exponential of this. Whichever way you do it, you have the same answer. Okay, so if you run this, you can print x and y. What can you see? X interval onto this, and then y, same result. But what's the difference? The vectorized code is very fast, quite faster than the scalar code. So least comprehension still results in scalar code because we still have explicit slow Python for loops operating on scalar quantities. The requirement of vectorized code is that there are no explicit Python for loops. In other words, for you to have a vectorized code, there must not be any for loop in your code. Let's see an example here. What I've written here, this scalar code, can be recondensed into a list comprehension, which is shown here. X equals np dot array minus 1 plus delta x times I for I in range n. And then what is y? Np dot array, np dot exponential minus xi for xi in x. Now, here we are working on arrays, but for the mere fact that we have explicit for loop inside this array operation makes it a scalar code. Let's see, we run it, same result, minus 1 until 1, and then the value of y is same. But what's the difference? This code is still a bit faster than the raw for loop, but it is not as fast as the pure vectorized implementation. So this is still a scalar code or scalar implementation of. So vectorization is very important for speeding up Python programs that performs heavy computations on with arrays. Moreover, vectorization gives more compact code that is easier to read. And vectorization is particularly important for statistical simulations, also for deep learning. So when we deal with very large amount of data and then we work on arrays, um, it is very advisable for us to vectorize all our code as it makes it run faster and more efficient. Okay, lastly, let's look at this function that I've defined here that returns x raised by 4 times numpy that exponential minus x. And then we want to use a vectorized form. We simply call x as clean space, and then we call the function of x. What do we have? Run this code and print. You see, print y. What is the shape of y? Y gives us 100 one-dimensional array. So this basically gives us example how we can also vectorize our functions. Lastly, before we come to the end of this video, here I want to show you some other operations in NumPy. We have mp.zeros, and you pass in the dimension you want. It returns, you can either print this way, print a that returns the array this way, or if you put in a in the command line, it gives you and tells you it's an array. The best form of it is just to use the print a. Also, we can create an identity matrix of 5 by 5 by simply calling np.I of 5. And if you run what we have, print A, it gives us this. There are very many operations in NumPy array. If you want to gain access to them, you simply call help on np because I've imported NumPy as np. So if you run this, it gives you detailed description of the package, the NumPy package, and it goes down to tell you give you examples, gives you all the sub packages and all the various modules that we have contained in this package. Okay, so you can take your time to go through them. You will see illustrations, examples, how you can use them. With this, we have come to the end of this video. If you have any question, please drop it in the comment section. Like my video as a way of encouraging this content. Share this video. And if you have not subscribed to my channel and you're watching this video, please subscribe to my channel and also click the notification bell to get notified of my new upload. Until then, I will see you in my next video.